you're effectively mixing together. So when you take the glycine buffer, when you mix the other three things with it, you're diluting that glycine buffer. And you're going to dilute it by a certain dilution factor. So the dilution factor is equal to the final volume that you produce as the total divided by the volume of the particular thing you're interested in. So in relation to the buffer, final volume is 200 microliters, because when you add all these things together, you have 200 microliters of solution. 75 microliters of that is the buffer. So the dilution factor is 200 divided by that 75, which is 2.66 reoccurring, which is your dilution factor. Okay, and what this means is that the concentration of the buffer in the final mixture, the initial concentration it was originally, divided by that dilution factor. Yeah, that dilution factor is being applied to the concentration of the buffer that was originally used. So the buffer concentration is now 2.66-fold lower than it was before, which is 2.81 millimolar. Okay, so whenever you mix things together, you're likely to eventually end up diluting them. And in this case, you can work out the final concentration of the buffer by either determining the dilution factor or using equations to do it. All good? Okay, so good news. There's a whole other practical we've yet to discuss. I thought you'd be happy. If I find this one. So, the other practical deals with fatty acids. So, PKU deals with amino acids analysis. The other practical deals with fatty acids analysis. And what we would do, is effectively extract the fats from different food substances and compare them. To extract the fats, one of the simplest ways of doing it is to do something called a bulk extraction. And it was named after the guy who developed the procedure way back when in the early 1950s, I think. You take your sample, you mix it up with a bit of aqueous solvent, and then you add some chloroform methanol mixture, a 2-to-1 mixture of chloroform methanol, and you mix it all together. And effectively what you get is phase separation, because like phase, the chloroform is insoluble in the aqueous phase. So you mix them and they all blend together, and then they'll separate back apart again. And as they separate, anything that's more soluble in the organic phase, like fatty acids, will move from the water-soluble phase into the organic phase. And you can take the organic phase off, and you just remove the fatty acids. They'll partition into the organic phase. It's a very quick, easy method of extracting lipids from biological materials. Once we've extracted those fatty acids, we're going to use GCMS, gas chromatography mass spectrometry, to study them. So what we do is we take that triglyceride. So they exist as triglycerides. You've got a glycerol backbone, shown here, so these 3 carbons, with 3 fatty acids stuck to each of the carbons. We mix that with acidified methanol. So you've got methanol with an acid catalyst that saponifies or hydrolyzes off the fatty acids from the glycerol. So it releases the glycerol and also releases 3 fatty acids. 1 from this carbon, 1 from this carbon, and 1 from this carbon. And it methyl-esterifies the carboxylic acid group of that fatty acid. So you add a methyl group to the OH group. That reduces the fatty acid's ability to hydrogen bond with itself. Because you've got fewer covalent bonds, it makes the compound more volatile. And if it's more volatile, it's more easy to convert it to the gas phase. And that's what we need to do for GCMS. Okay, so we'll extract the lipids, convert them all to methyl esters, and then analyze them by GCMS. So GCMS generates two types of data. The first thing it generates is a chromatogram. So GC, the gas chromatogram, separates them by time. And so as time goes by, each of the fatty acids will come off the column and go into the mass spectrometer. When it goes into the mass spectrometer, it gets analysed, and the number of ions increases. And so the chromatogram plots the number of ions in the mass spectrometer at any given time against time itself. And so each of these peaks here represents a compound coming off of the GC and going to the mass spectrometer. So this one comes off first, followed by this one, followed by this one, so on and so forth. And the peak area, the area underneath these peaks, represents the concentration of each component. So this is in greater concentrations compared to this, and this is in greater concentrations compared to this. These two are almost equivalent concentrations, and these two are almost equivalent to the same peak area. So the peak area under the chromatogram tells you about the concentration of each fatty acid in that mixture. Within each peak, you also have a mass spectrum. So each peak generates a mass spectrum in the mass spectrometer, and the mass spectrometry data is unique for the chemical nature of that compound. So you can look at the mass spectrum, and it will be unique for this compound. Each of these things only occur, these peaks and masses only occur for this particular compound. So this is our sort of data. You've got a few peaks, and there's a few peaks on this end, and these are 5 different samples. These two look quite similar to each other. These look similar here, but this one's got more peaks here, and this one's got a lot of peaks on this end, but nothing much up here. And each of these peaks has a specific retention time. So 19.5, 17.4, 21.2. And so I've generated for you the peak area, 5 replicate extractions of each sample. So for the analysis, you've got to do a number of things. The first thing is identify which peak is what fatty acid. If I stop this, I'll show you what's on canvas, because that will make more sense, I think. If I go into the PowerPoint and go here. So on canvas, we have a file entitled GC Spectra by Retention Time. Okay, so I've gone through the chromatograms and found the retention time of all the different chromatographic peaks. And every time we've got a chromatographic peak, I've taken a picture of the mass spectrum at that given point. So at 12.5 minutes, the mass peak gave this mass spectra. At 15.12 minutes, it gave this mass spectra. At 21.2, it gave this mass spectra. Now, key peaks in this mass spectra are the one at the high end. Okay, ones at the bottom end are probably shared between lots of different fatty acids. It's the ones up here which are going to be more unique for each different fatty acid. So you've got, for every retention time where there's a chromatographic peak, a mass spectrum. Another file that you have on canvas is here. It's referred to as the GCMS NIST identifications. So NIST is the National Institute of Standard Technology based in America. And effectively what they did is in the 1970s, they basically started synthesizing chemically all these pure compounds and throwing it at mass spectrometers to see what they look like in a mass spectrometer. And so they've got archived mass spectrums from different compounds. So if you get into decanoic acid, methyl ester, and throw it at a mass spectrometer, this is the mass spectrum you'll get. If you take octanoic acid, this is the mass spectrum you'll get, and you can zoom in to find what masses you see in this mass spectrum. So by comparing the mass spectra here on the NIST of known fatty acid methyl esters to the spectra at different retention times, you can work out which retention time is octanoic acid and which retention time is decanoic acid, etc. So by doing that comparison, you can identify which chromatographic peak in the data represents which fatty acid. Okay, so far so good? Okay, next fun part. So, allows you to identify the fatty acids which have been extracted and analysed during the analysis. The next thing you have is we took 10 samples, so 10 food substances, so coconut, hazelnuts, peanuts, almonds, rapeseed, sunflower oil. We did 5 different lipid extractions from each sample. So we extracted each sample 5 times. We analysed by GCMS, and here's the retention times of the peaks we saw in GCMS. And we have the same retention times for every single sample. So we've recorded the same retention times for each of the 10 different samples and each of the 5 replicates. And then each of these columns here represents the peak area associated with each retention time for each of the 5 replicate extractions. Okay. So here, obviously, this peak here seems to be the most abundant. In this one, it seems to be this one. Now, in principle, we don't want to have 5 sets of data for every sample. So we want to just use the average. So we want to take the average of these. So we've got one value, one number for each retention time or fatty acid for each sample. The problem with that is that if you look at the values across, let's take this one for example, one fatty acid in 5 different extractions from the same food, you get very different levels of that lipid in terms of the numbers. That's because this extraction here worked a lot more effectively and put out more fats in this extraction here. Generally, the numbers here are larger in this one than they are in this one. And that means you can't take the average of those as they stand. It would make no sense. So you've obviously extracted more fat in some samples than you have in others, or some extractions for the same sample as you have in others. If I quickly show you I've got a simplified version which might be more sensible. So I've created a simplified version of that same data. Ignore this over here for now. So here's a simplified version of that data. So you've got coconut or hazelnut, doesn't matter what it is. You've got one sample extracted 3 times in this instance. And you can see, and you've got 4 different fatty acids being measured in all 3 of those extracts. And this extraction seems to have worked a lot better, for example, than this extraction, because the numbers are all higher in this extraction than they are in the comparative peak for this extraction. And so you can't just take the numerical average of those 3. So what we're going to do is we're going to create a normalized value. And the easiest way of normalizing this data is to effectively, first of all, work out the total peak area for each individual extraction. So add up all the peak areas for that extraction, add up all the peak areas for this extraction, and all the peak areas for this extraction, and report them. And as you'd expect, it shows you that this extraction pulled out almost 3 times as much fatty acid as this extraction did. So if you want to compare these then, what we can do is report these values as a percentage of the total. So if we report this value divided by 132 times 100, because 132 is the total amount of fat. Yeah, it's what don't you like? Put a bracket there. And if we report this value as a total of percentage of 92, and if we report this value as a percentage of 295, And once we've done that, we can copy and paste that down all the other Excel functions. Now, they're much more comparable because they've all been internally normalized to the total amount of fat. So it doesn't matter that we put out 3 times as much fat in this extraction as we did in this one. Because when we report the individual fats as a percentage of the total, it means you can compare them. Once we know that, we can then take the average of those 3. Cool. Thank you. So we take the average of those 3, and we can produce the standard deviation. Just do. You can see the standard deviation is quite small, suggesting that normalization has counted for the variation extraction. Okay, so go back to the instructions. So as part of the report, one of the things I want you to do is use the NIST database or NIST spectra to determine which potential times represent which fatty acids. Convert the raw fatty acid data to percentage of the total area for each of the extractions per sample, and then produce a bar chart to show the average and standard deviation for each fatty acid in each fat or each food substance as a comparison. So take that raw data, normalize it, and produce a bar chart of the average with standard deviation as the error bars to show that data. The next thing I want you to do is something called a hierarchical cluster analysis, which I will quickly show you here. So, what you'll do, if I could spell it would help. Let's move that over. Move it back over here. Okay. So, let's spell things properly. Coconut. Hazelnut. Right. So you're going to have 10 samples eventually, and I want you to arrange 10 samples in rows. Each row represents one of the 10 samples, and then each column represents the mean, the average percentage for each fatty acid methyl ester. So this might be octanoic acid, this might be dodecanoic acid, octadecanoic acid, pentanoic acid. But these are the averages of that particular fatty acid in that particular food substance. And you need to arrange them in this format because you're then going to put them into SPSS. We haven't had quite enough fun with SPSS yet. Okay? If I take you to SPSS then, where's SPSS? There it is. So you end up with the data in SPSS, and I've done a record of the sample names over here just to be annoying. So we've got the different food substances and the percentage of the total fat for different fatty acids. And if you really want to, you can of course name those fatty acids if you really want to. But you don't need to, you can leave them blank. It's not going to make a difference. But it's good to have a list of the different names of the different food substances, and you'll have 10 of them. And so that's your food substance, that's the percentage of one fatty acid, another fatty acid, etc. Bizarrely, I've made greater than 100%, bizarrely, but there we go. Okay? So we arrange the data in this format. And there's in the pro forma for this practical write-up, there's a YouTube video link that shows you how to do this. So if you don't catch it now, don't worry. But what you're going to do is going to analyze, and you're going to classify the data using a hierarchical cluster analysis. So when you do that, originally, let me just move these back over because it remembers where they were from before. In this instance, we've got variable 1 to 5 are your fatty acids information. So that's become our variables. That's what we're going to use to do the clustering. Variable 6, where we've labelled different food substances, is the variable we're going to use to label cases. So it's just there for labelling. Does that have anything interesting in it? Usually this is clicked off, so you just click it on to tell it to draw a dendrogram and decide whether you want to be a vertical one or a horizontal one. Doesn't matter, personal preference. In the method, if it's not already chosen, you need to pick Ward's method. And then you just tell SBS to do its job. At which point, of course, SBS stops showing you what I was clicking to on screen. So we'll share the output screen. But all this gobbledygook, which you don't particularly care about. What you care about is the dendrogram that's produced. So this is a dendrogram that's produced as a consequence of that. It's sort of like a phylogenetic tree based upon lipid composition. So it's clustered things together, or closer together, dependent on how similar they are in terms of the lipid content. So certain walnut, because the branch between them only goes back a short distance, are very similar. The next most similar example is margarine, because it's linked to that branch by another branch here. Hazelnuts, by definition, are very different in terms of lipid content, because the branch that links to the hazelnut goes all the way back before it makes a new branch to the hazelnut. So where the 10 samples clustered together defines which are more similar and more distinct from each other. And so I want you to produce that dendrogram and effectively comment on it. So, last but not least, I will show you what the form looks like, just to try and convince you. So, in point of fact, it's got the wrong module code. I'll get there eventually. So you've got a general introduction to fatty acids and GCMS. Just to talk you through it again. The method and protocol that you would follow, and I'll try and put a video of this on Canvas as well, of me doing it and messing it up. You've got, this is where the marks come in. So all I need are the results and discussion for the actual writer. So you've got results basically saying work out percentage content and draw me a bar chart with median standard deviation. Use hierarchical cluster using SPSS, and here's a YouTube video that will tell you how to do it. And then answer the questions. Comment and give an explanation of the nature of that distribution, that hierarchical cluster, why are different samples related similar to each other. Look at the method protocol and figure out why it uses sodium chloride. Look at why HPLC is less useful as a method of analysis of lipids. Talk about semi-quantitative analysis and what that means, and effectively interpret this mass spectra of this fatty acid. Tell me where these ions come from. And that's it. That's all you're expected to do. 10% each. Okay. I've set the deadline, I'll suggest the deadline of the 30th of April. So after Easter, at the end of the last 2 weeks of teaching. I realise this is the same day as the last MCQ test, I think, for this module as well. But I'm confident that you'll all avoid submitting on the day of the deadline at the final point available, because you can submit before deadline. So it's just a matter of organising time appropriately. Are there any questions? Are we all happy? Happy is pushing it, but